We learned in the videos on torque that torque, it equals, let me actually draw a picture so you remember what we're talking about with torque. So let's say, so that's the arm. Let's say right here is kind of what its pivot is. That's its pivot. And let's say that I'm putting a force. Let's say I'm putting a force right there, and it's perpendicular to this arm. And let's say the length of this arm is r, and that this force is, well, let's say that this force is F. So we know that the torque is this force times the distance, right? Torque is force times the distance. And then we also know that what is force? Well, that is equal to mass times acceleration times distance. So torque is equal to mass times acceleration times distance. And then so what is acceleration? Well, that's equal to mass times change in velocity over change in time times distance. Right? So that we learned all that from our torque chapter, and you might want to review it just to get an intuition of what torque is good for. But in general, if something isn't spinning, you apply torque and you'll get it spinning. Or if something is spinning already, if you apply torque in the direction that it's spinning, it'll spin faster. Or if you go in the opposite direction, it'll spin slower. And what I'm showing you here is that what happens if you apply no torque? Well, if you apply no torque, then we know that this quantity is 0. Or another way to think about it, actually, why did I write D? This is, well, it couldn't be D, but I shouldn't have called this R. This should be D. So if this is 0, if we're applying no torque, right, what do we know? We know that the change in velocity over change in time times this distance won't change, that this quantity is 0. So we know that the velocity times the distance is going to be a constant. And that comes from what I just talked about. I sometimes almost feel like it falls out of Newton's laws, but it applies to spinning. An object that's not spinning will tend to not stay spinning, and an object that is spinning will tend to stay spinning. So in this case, if this point right here, so we're in a case where there's no torque, so this force is 0. There's no force applying here, and whatever this object's velocity was, right, is tangential velocity. It's going to stay that velocity, right? It's just going to keep spinning at that velocity. If I apply more torque it'll go even faster. If I apply less torque, it'll slow down a little bit. But we know that this velocity times the distance is constant. And actually, I don't know why I took this m out. We know that the mass times the velocity times the distance is constant, right? So what does that tell us? Well, we learned in the angular velocity video. My mind's a little slow today. That what? Angular velocity is equal to velocity divided by the radius. And in this case, the radius is this distance. So we could also write it as velocity over distance. And when I talk about radius, it's just the radius of the circle that you're kind of spinning around in, right? This could be the circle up here. So this d, that's the same thing as the radius. I'm just switching letters to confuse you. But let's see if we can write something, if we can change this expression to include angular velocity. And you'll see where I'm going in a second. So let's solve for v. So let's multiply both sides of this times d. So you get dw is equal to v. Right? I just took this d, put it on this side. So let's write that here. M times dw, right? I just replaced the v, times d is equal to a constant, assuming that we have no net torque on the system. And so what does that get us? Well, that gets us m times the angular velocity times d squared is equal to a constant. So what does this tell us? This tells us the mass of an object spinning. So let me rewrite this, because I think so what we know is that the mass of an object spinning times how fast it is spinning times the distance to the center of its rotation, and actually I'm going to change that d to an r. I don't know why I even used d to begin with. Times that squared, that's going to be equal to a constant. assuming no net force, no net torque. And another way of looking at that, if we just wanted to go to angular velocity from the get-go, we could have said torque is equal to mass times change in velocity times change in time times the radius to the center of where you're rotating around. And change in velocity is just the same thing as mass times change in angular velocity times r, change in time, and then there's another r, that's this r, right? Because velocity is angular velocity times r, and we're assuming r doesn't change. So any change in velocity is just going to be a change in the angular velocity. And then we would get the same thing that we just got here. If we have no net torque, we're going to have no change in angular velocity, so angular velocity will be a constant. So you'll get mass times angular velocity times, and then you have this r and this r, times r squared is going to be equal to constant. Where am I going with all of this? Well, let's think about something. Let's say that I have some object traveling in a circle. I do everything for a reason, and you'll see my reason right now. Let's say that this is some kind of, well, I think it'll make sense in a second. So this is, I don't know, let's say this is some type of retractable pole, and I'm an ice skater. And I'm not using the ice skater's body right now because it'll become complicated. Let's say this is some type of robot arm, right? And that's its joint right there. And it's holding a mass out here. It's holding a mass. And this is neat because after this concept, you will understand what goes on in figure skating. And the Olympics, oh no, the Winter Olympics are over, aren't they? Well, anyway. So let's say that this object is spinning around at some rate, right? Some rate. Let's say it's spinning around at, I don't know, 10 radians a second. 10 radians a second. That's its angular velocity. And let's say right now its rotational distance is, I don't know, let's say it's 10 feet. So let's say this is spinning on a this is an object that's spinning on an ice skating rink, I guess is a good way, because you don't want friction and all of that. So what's its current angular momentum? So that's what this term right here is, angular momentum. So what's its current angular momentum? Well, it's mass times 10 times, right? 10 is its, actually let's make this radius a different number. Let's call it 8 feet, just so you know what I'm doing. So its angular velocity is 10, and then its radius is 8, so times 64. So it equals 640 times the mass. This is its angular momentum, right? Now what happens if this arm, for whatever reason, shortens, and maybe it does something like this. The arm kind of bends, and then the mass comes here. It comes in closer to the center. Let me write that in a different color. The mass comes closer to the center. So now the radius is 4. But I've had no net torque on the system. All I've done is change how far it is from the center of rotation. How much faster is it going to spin now? Well, let's think about it. Its angular momentum won't change. This is a constant, which is its angular momentum. That won't change. So we now know that the mass times the new angular momentum, we'll write that the angular momentum 1, times the new distance squared, times 16, is also going to be equal to 640 m, right? The angular momentum doesn't change. Let's cross out m from both sides, and then divide both sides by 16. We now have that W1 is equal to, 16 goes into 640. So what happened? Originally, I was going around at 10 radians per second. When I halved the radius, when I got half as close to the center of my rotation, I'm actually spinning around 4 times as much. And that's because this term is a quadratic term. And this makes you probably have observed this behavior before when you see the ice skater skating around and they're spinning with their arms wide open, and then they pull their arms in and they go a lot faster. And that's because their angular velocity, or the rate at which they're spinning, is proportional to the square of of the radius around their axis of rotation. Anyway, I hope I didn't confuse you, and I'll do some more problems with this in the future, but I've just run out of time. See you soon.